Welcome to part two. We've already talked about igneous rocks and like what rocks are and what minerals are, that kind of thing. So we're going to talk about the last two rock types and then just a few more little details that I want you to think about. Um, Sedimentary rocks, how do they form? Well, first of all, we need some sediment in order to make our sedimentary rocks. So sediment is produced from the physical and chemical weathering of rocks. So this gives us pieces of rock. If you go to Starved Rock State Park for a hike, for example, you'll notice that rock is falling off the cliff. It gathers in the bottoms of the canyons, and then the streams take it away, move it out to the Illinois River, where you can see mud in the water. There's sand on the bottom. Um, those pieces of rock we call clasts. If the rock chemically breaks down, we can get clay minerals, which is a whole set of silicate minerals. And we can also get material dissolved in the water, and so those would be the dissolved ions. Those materials are then moved away from the original location. They may go a short distance, they may go a long distance, but this process of erosion and transportation will then move that sediment to a new location. When the sediment gets dropped off, that's what we call deposition. And deposition can occur in a number of ways. We can get those pieces of rock, those clasts, deposited. Material that's, and we can also get deposits of clay, which kind of count as clasts as well. But they're sort of a special category. We can also get chemical precipitates. So when those dissolved ions come out of solution, one way to do that would be to evaporate the water. Another way would be to have a kind of a chemical reaction of some sort. Those chemical precipitates become sediment as well. And then our third kind of deposition occurs when life collects material from its environment, creates a living organism, and when that living organism dies, that material becomes sediment. Or when it goes to the bathroom, that's sediment as well. So all that material counts as sediment. Now, once deposition has occurred, that material could be picked up and moved again. So very often sediments get eroded and transported many, many times before they get to their final resting place. But once they do, they can be buried. And when they're buried, the pressure of burial can result in lithification. It's a little more complicated than that, but for our purposes, lithification is what we refer to as burial and cementation and compression. So once we bury things, we compact them. The water, the groundwater that might be running through there has very often dissolved minerals in it, which can be left behind. That all comes together as part of the lithification process. So that's the process where we turn those loose materials, those sediments, into a solid or semi-solid sedimentary rock. Some of our sedimentary rocks are not very well cemented. They can fall apart quite easily. So what types of sedimentary rocks do we have? Well, when we classify the sedimentary rocks, we put them into two broad groups. One group is made of pieces of rock or clay. So gravel, sand, silt, and clay, those are the clasts. So we call those clastic sedimentary rocks. They're also called sometimes detrital sedimentary rocks. And those rocks are classified based on the size of their grains. And then we have the non-clastic sedimentary rocks, which has a lot of ways they can form. But the two kind of generalized ways they form are through chemical processes like chemical precipitates or from biological materials. And there's a list here of some of the common types of non-clastic sedimentary rocks. The most common type of sedimentary rock is limestone and dolostone. Those are biological or chemical in origin. They're made of calcium carbonate. Dolostone is calcium carbonate with a little magnesium in it. So That's limestone. Then we have chert, which is made of silicon and oxygen, which is basically quartz, but in this case, it's a chemical deposition. They can also form biologically. There are some very tiny organisms in the ocean that make their shells out of silicon and oxygen, and that can turn into chert. Evaporites, as the name implies, form when water evaporates and leaves its mineral content behind. Two very common evaporites are gypsum and rock salt. And if you're thinking rock salt, yeah, that's the stuff you put on your food. So that is a chemical precipitate from, very often from seawater, but it could also be from a lake like the Great Salt Lake. There's a huge salt mine, or several big salt mines by the Great Salt Lake. They actually let water come into their pit and then evaporate, and then they collect the salt. So it's kind of an artificially created rock. And then the last one on the list is coal. We saw a chunk of coal in class last week, and coal is made strictly of biological material. It's made of wood from dead plants. So here's a chart in your book that kind of lists some of those common rocks, talks a little bit about their origin, and we'll be looking at those in lab this week. So some of the really common properties of sedimentary rocks. They're a very important source of economic minerals in our area. That's what we mine for silica sand. We also mine limestone in our area for gravel. And we used to mine coal to heat things. So the strength of sedimentary rocks varies enormously with the sediment type, the cementation. There's a lot of variety in this group, which you will see in the lab. If you go outside, sedimentary rocks you can see have layers, and that can provide some weaknesses in a specific direction along what we would refer to as the bedding planes. Water can flow through this rock quite easily in some cases. So again, it depends with the sediment type and the natural cement that's holding those sediments together. Some of the rocks are subject to dissolving. Limestone is the kind of the poster child for this. It's the notable case. Most of the caves that you find are forming when limestone dissolves. So that brings us to our next rock type, the metamorphic rocks. Metamorphic rocks form from existing rock. So if you have a sedimentary rock or an igneous rock or even a metamorphic rock, and you subject it to heat and pressure, it can alter that rock. And there are a number of environments where this can occur. You can get straight up heat by being in contact with some molten rock or with warm water that's moving away from an igneous intrusion. So igneous intrusions, there's a relationship here. They can cause contact and hydrothermal metamorphism. If you bury rocks very deeply, instead of just turning into sedimentary rock, for example, you can put enough pressure on them to create metamorphic rocks. This can also happen along faults. And then the heat associated with, or the pressure associated with burial often comes with a lot of heat, and that will give us what we call regional metamorphism. One of the things that results from the intense pressure can be what we call foliation. So very often metamorphic rocks, when you look at them, you will see that the minerals are all lined up due to that high pressure. And we'll take a look at a picture of that in just a moment. This is a lovely graph that shows you temperature going across the x-axis and pressure going down the y-axis. And the reason they go down in this case is because the pressure is associated with depth. So the deeper you go, the greater the pressure of material above you. And then it shows you some different types of metamorphic rocks associated with those conditions. If it's mostly temperature, you're going to have the contact metamorphism. If it's a mix, that's where you get the regional metamorphism. And we'll take a look at some of these labs downstairs. If you look at one particular type of sediment, So if you start with some clay, we'll see in class this week the sedimentary rock that forms from that is called shale. So under low pressure and temperature conditions, you get a sedimentary rock. If you crank up the heat and temperature, or the heat and pressure a little bit, you get a low-grade metamorphic rock that we call slate. And it looks very much like shale, the rock made out of clay, except it's much harder and it's much more dense. If you increase the pressure and temperature a little bit more, you'll get an intermediate rock that they don't list on here called phyllite. It looks like slate, but it's kind of shiny. If you increase the pressure and temperature enough, the minerals will actually become visible. So what's happening in the metamorphic process is that new minerals form and grow. And when you get to this intermediate grade, the minerals are big enough to identify. And at that stage, we call the rock a schist. If you increase the pressure and temperature even more, the minerals get larger and the rock actually starts to look, in terms of its minerals, kind of like an igneous rock. The big difference is the foliation, which means the minerals are all lined up, and we'll take a look at that down in lab. But otherwise, mineral content-wise, it's a lot like an igneous rock, and that's because the pressures and temperatures are similar to those in an igneous environment. And so this is to give you an idea. This shows it a little bit, low grade and high grade. This shows it very clearly. We can go from low grade to high grade in our metamorphic rocks. So the rocks that we'll be looking at down in the lab, low grade slate and phyllite. We'll look at a few medium grade schists, and we'll look at a high grade gneiss. Depending on the mineral composition, sometimes the minerals aren't able to line up. And the notable examples of that are marble and quartzite, because they have kind of a uniform mineral composition, as does anthracite, which is really just organic material. We don't see the minerals lining up, and so these rocks are called non-foliated. Hornfels is listed here, but we don't have it in the lab. It is a contact metamorphic rock, and therefore not much pressure, no foliation. We grade the metamorphic rocks based on its type of foliation, as we saw in this previous slide. But we can also use the size of the mineral crystals. Generally speaking, bigger crystals, higher grade. And there are certain minerals that show up that we call index minerals that give us an idea of how much metamorphism has occurred, because different minerals are stable at different pressures and temperatures. So that's a lot to know, but we'll be looking at these rocks in the lab, and you can read more about them in the book. So I'm just trying to highlight some things. Now, what can we use metamorphic rocks for? Just like the other two sources of economic minerals and economic rocks, the interesting thing about metamorphic rocks is they tend to be pretty durable because of the high heat and pressure associated with their formation, except the foliation, the layering that we find due to the high pressure, can cause there to be weakness in one direction. One of the things that allows you to do is break this very hard rock into thin layers and use it as roofing material. And so the roof on this building is made out of that low-grade metamorphic rock, slate. We're going to wrap it up. There are some more slides that you can look at, but I wanted to just mention the rock cycle, which I would really like you to look at in the book. It shows how the different rock types form and how they relate to each other. And it reminds us that each rock can be turned into one of the other rock types. The other things that we look at a little bit are the strength of the rock materials. That's going to be important to engineers, for example, building on the rocks, and for folks studying faults, like when is this fault likely to break? That's dependent on the strength of the rock. And that's about all we have time for. So That's it.